Hi everyone, my name is Nolan, and in this presentation I'll be discussing the effect of some broad-scale atmospheric effects on radio frequency signal attenuation. What I mean by broad-scale effects is that I'll be focusing on mainly wireless channel effects and relatively general cases, and less on specific issues that might be encountered with particular equipment. And so mostly this comes down to discussing weather. I tried to break things down into fundamental categories. What we'll see ultimately is that matter is what affects signal strength. Things get in the way and cause signals to lose energy. We'll also see that different frequencies are affected differently by matter obstructing channels. Distance also comes into play because if a signal has to travel through more matter, it will lose more energy to that matter. The same is true with density of materials, in that generally speaking, the more dense something is, the more it will attenuate a signal. Reflection, scattering, and refraction also come into play in determining where some signals end up if they aren't attenuated completely. This audience is probably already familiar with how many of these things affect signal strength, but I'm hoping to give a relatively informative overview, and hopefully that includes some new information for you. The normal atmospheric phenomenon that attenuates signals most is rain. Snow, ice, and other precipitation also fall under this category as I'm explaining it, but they are generally considered to be less common and less impactful for most communication applications, at least wirelessly. So I'm focusing on rain here. As you may know from the operation of microwave ovens, water absorbs energy from some frequencies of electromagnetic radiation. The size of water molecules, in addition to their extreme polarity, makes them susceptible to movement when exposed to varying electromagnetic fields. Those fields in this case are our wireless links. The attenuation due to the absorption of energy by rain through creating heat is called rain fade, and it usually is considered to be significant in frequencies around 11 gigahertz and above. It's also significant between 3 and 11 gigahertz, but not quite as much. As if you take a peek at that graph, the attenuation is much less significant when you're under 10 gigahertz. But for common wireless links in that kind of 11 to 50 gigahertz range, rain fade is a very serious consideration, and it has a little peak at around 12 gigahertz, and then some other serious attenuation in the range from kind of 20 to 27 gigahertz as well. Of course, going back to the idea that how much stuff is in the path of a signal determines how much it is attenuated, how large of a rainstorm and how intense the rain is affects how much the signal is attenuated. Thinking about, again, density and distance over this wireless link. For practical scenarios, historical rainfall data is used to determine how much buffer for rain fade should be allotted in a link budget. As the visual there shows, attenuation can be quite significant in heavy rain, and the longer the path through a storm, the more the signal is going to degrade. Both terrestrial and satellite links are heavily affected by rain fade, but satellite links usually operate more in the frequency bands that are most effective, at least over long distances. And these are frequencies such as in the X band, which is from 8 to 12 gigahertz. Not surprisingly, radars also typically operate in the region from 1 to 50 gigahertz. They want to see what kind of particles are in the air after all. With some storms, with heavy rains being as tall from the ground to the top of their storm as around 7 kilometers. According to this figure, the attenuation could be very significant if you had some really heavy rains, probably around 20 decibels. Heavy frequent rain in tropical climates is especially troublesome since the attenuation is so severe. And based on the required quality of service, decisions are going to be made about how much extra power can be available for these links. And that's going to inform how big of a satellite you want to launch with specific power capabilities, etc. Additionally, diversity methods are often implemented in these communication links. Not very surprising there. Usually this takes on the form of things that we talked about in class, actually. Spread spectrum methods. It's all about frequency diversity. And so this can be CDMA and frequency hopping. Additional error correction is also used. And one thing I don't want to forget is that in addition to just attenuation through heating up that water, scattering through moisture droplets also occurs and serves to contribute to further fading. So that signal is going to hit those water molecules and spread out a little bit, and ultimately that the energy is going to be lost in some way, but there's going to be some spreading associated with bouncing off of those, reflecting off of those water droplets. Ultimately, when designing appropriate links and specifying equipment, rain fade is a serious consideration, and that has to do with weather, location, and it's frequency dependent. Not so much of a big deal below that 3 gigahertz mark, but above that, it's a really big consideration. Temperature and humidity are generally seen to be linked quantities when it comes to observing their effects on signal strength. Since the amount of moisture that the air can hold increases with temperature, often a greater absolute humidity is present in warmer air, which may explain slightly attenuated signals. The idea here is that, again, with a higher concentration of water in the atmosphere, there will be some attenuation at higher frequencies, those frequencies which are affected by the water. Cold air, while being more dense, is also typically lower in moisture content as compared to warm air. In one study I looked at, the effect of absolute humidity was much more prevalent when testing in cold temperatures, and an increase in humidity was correlated with an attenuation in signal strength, which is not very surprising. Referring to the plot down below, there is a good correlation between an increase in temperature and a decrease in signal strength, although the attenuation is really quite small at this 2.4 gigahertz frequency that was being tested, especially considering and compared to the potential rain fading effects that we talked about earlier with attenuation up to 20 decibels in really heavy rain. This is, I mean, it's really only around 1 or 2 dB. Temperature can also influence the noise level of sensors, and an increase in temperature will yield an increase in noise, which should be taken into account. Overall, higher temperature and humidity yield higher levels of attenuation. That's in general. But the effects of both temperature and humidity are relatively small. And it's of my opinion, looking through several studies, that these temperature and humidity effects are not going to be terribly significant and could be easily overshadowed by other things. We should also probably categorize our atmosphere. Down here on the left, you can see this image of the layers that the atmosphere is broken up into. What we're going to talk about are the troposphere, which is down at the bottom where all the weather happens. We're going to kind of skip the stratosphere area where there's a bunch of ozone and also talk about the ionosphere. And the ionosphere is the region where the sun's solar radiation breaks the air, because it's such high energy, into ions. And these charged ions can have quite a big influence on radio signal propagation. So the first thing that can happen is attenuation. The ionosphere will attenuate most signals, at least to some degree, usually quite significantly. And that usually point kind of brings me down to this lower image. This is a comparison of nighttime and daytime ionosphere layers. They're broken up into these layers, and the layers do have different effects. I'm not going to get into that in this presentation, but because the sun is shining in the daytime, there are, generally speaking, more ions present, and in the daytime, signals are usually attenuated more, and so you actually have less propagation during the daytime from refraction off of the ionosphere. And that's kind of the general idea here, is that many frequencies will be refracted when they get to these layers of charged ions. And that refraction causes your wireless signal to actually point back down toward the Earth. So you can cover quite a large distance as long as your signal is not completely attenuated. Your signal can refract off of the ionosphere and can travel quite a ways, which is pretty cool. These are called sky waves rather than, say, a ground wave, which is going to travel across the ground, not very surprisingly. So that's kind of how the ionosphere works, and I thought it was pretty interesting, at least, that the propagation of these waves can change drastically from daytime to nighttime, because those ions recombine and are no longer present, and that D layer and those two F layers combine to make that larger F layer. And what happens here is that certain wavelengths in lower frequencies, like in AM radio, for example, can actually propagate farther at night, which is pretty cool. In some places, they actually have to turn off certain AM stations because there's too much interference at nighttime. And that's just because those signals are not getting attenuated as much as they were in the daytime, so they can propagate pretty darn far. So that's kind of an overview of the ionosphere. We should also talk about the troposphere. And the troposphere is that lower layer of the atmosphere where all the weather happens. You kind of have a few different modes of wave propagation here. The first is a ground wave, and that's when, due to different densities low to the ground, waves will follow the curvature of the Earth and can propagate beyond the horizon, where they would normally shoot straight out into space if Earth weren't there. So that's the first kind of thing, the ground wave. Then you have other types of refraction that come into play, and usually this kind of propagation is caused by an inversion layer, where a cooler air mass will move near to a warmer air mass. Sometimes it comes down from above, and you get some stratification. You get some different layers of different densities stacked up in the atmosphere. And when that happens, if you look at this picture down on the left, you can actually have what's called ducting. And if you get a warm air sandwich, that because of the different indices of refraction, that radio wave can actually propagate like fiber optics, only not quite as well as that, but effectively the same idea. It's kind of like fiber optics through this channel, through this duct in the atmosphere, and you can get radio waves that would travel much farther than they ever normally would under normal propagation scenarios with what's called ducting. And this is pretty common in actually a couple of months of the year, in July and August, depending on where you live, which is pretty cool. You can get really in certain frequencies anyway. Usually those lower AM, C band, stuff like that. Those lower frequencies, but I think it's pretty cool ducting. You also have some multipath due to scattering, because the lower atmosphere is a very turbulent, active weather space. So you're going to have some components reflecting down from the sky. So that's kind of the troposphere. I'll just briefly run through the effects of wind. Obviously, in the atmosphere, wind does play a role, but it's not as much a direct role. I would say wind is a byproduct of the atmosphere moving around. So one place it does have a small effect is if you have a channel that has trees with leaves, with or without leaves, directly in the channel. The speed of the wind can make your signal be attenuated a little more. And the directionality does play a role, although that's a very case-by-case situation. So not really a broad scale effect, but wind does exist. That I would think more of it as turbulence in the air column if we're considering the broad scale effects. And again, refer to those tropospheric ducting and refraction effects due to changing air masses. So that's not so much of a broad scale effect, but something that is mountain diffraction, or really diffraction in general over any large things in your channel, especially with sharp edges, but even to some degree if something doesn't have a sharp edge. So signals can be diffracted down into mountain valleys, where otherwise maybe only a satellite signal would have been able to reach. There's going to be a considerable amount of attenuation, because that diffracted component is not going to be very large compared to the line of sight component, but it is still a pretty cool thing that if you don't have that line of sight or any reflected components of your signal, you can still get some signal if your conditions are right. And even in Vermont here with our very rounded mountains, there are components of wireless radio signals that are diffracted over mountains, and so sometimes you can get still good cell service if you're not directly in a line of sight of something, which is pretty cool. And if you want to look at some of the resources that I used, feel free. Thanks for listening.